Welcome to our lectures on the DC microgrid and the control system. We shall continue our discussion with the microgrid operation modes and its standard. So, that is something we require to work on it. So, we already have a grid code and all those things in a power system are quite standardized, but we require to form a standard for the microgrids. So, this microgrid operation modes we have already discussed in the introductory classes. We shall revisit it again and then we shall structure them into a different kind of operation mode, and control mechanism for the connected distributed generation of the microgrid and speed control of the classical distributed generator and control of inverter based distributed generator. So, these are the two methods we shall try to cover in our lecture. Now, the small and smart microgrid systems are under continuous development to the integrated massively renewable energy sources, and the micro generators and small energy storage allow the critical and the non critical loads in the control systems. The microgrids are small electrical distribution system that connect multiple customer to multiple distributed sources and with a storage element. The microgrid are typically characterized by multipurpose electrical power service communities that are connected via low voltage networks, right. So, those are things we have already discussed into our introductory class, but we wanted to revisit once we wanted to have a different kind of mode of operation. So, it is a great interest of that hybrid power system have the potential to provide reliable power supply to remote communities where connection to the transmission supplies are non-economical. So, first microgrid was introduced in India, that was in Sagodip, was a place of pilgrimage. So, that was not a great success story either, anyway that comes later. Different scenarios for future architectures of electrical systems recognize a fundamental facts that with the increasing level of distributed generation penetration, the distribution network can no longer be considered as a passive element or passive appendage of the transmission network. So, entire distribution system has to be designed or operated as a integral system. So, previously we had a generator and rest of the thing was a passive, but within a transmission distribution system also you have a source. So, we have to consider the whole as an integrated unit. When renewable energy sources such as PV, wind are connected, the power fluctuations of RES, that is the renewable energy sources, can be compensated by integrating the energy storage element. So, you can have a solar variation and fluctuation, wind variation and fluctuations. For this reason we require to have a storage element. The local controller have been employed in order to perform the independent and simultaneous control of the generated active and the reactive powers. Some new control capabilities has been developed in order to create new possibilities to manage the power system in the presence of the renewable energy based generator. With widespread implementations of the distributed generations concept is creating the region within the electrical distribution network with enough generation capacities to meet all or most the local loads. So, that is something we require to plan it. So, what is the capacity, installing capacity and what is the inhabited capacity. So, it should match either. So, if you have it should not be actually total mismatch, it then does not make a sense either. And such region is then, if it is a self sustainable energy, and thus they are to be said to be the microgrids. And so, recently IEEE standard 1574.4 depicts the main features of the microgrid system. Capable of operating in parallel with the main grids, that mean grid connected mode, or autonomously in isolation with the main grid, that is the islanded mode. Islanded operations of the microgrid system can bring several benefits to the distribution utilities and the customers. Such benefit include the improving customer reliability, resolving overpower problem, overload problem, resolving the power quality issues, allowing the maintenance of the component without the customer's interruption. These are the few things, that is the advantages of the microgrid. In microgrid, in the grid connected microgrid mode of operation, DG units generation is controlled to supply the predetermined amount of the active or the reactive power required for the fulfillment of the specified system requirement. For example, the peak saving, exporting power to the main grid, etc., when their peak power is there. So, that is something we require to plan accordingly. Any difference between microgrid total load and the active and the reactive generation of the DG's unit are absorbed or supplied by the main grid. So, you do not bother it. So, you just put it whatever extra to the grid. Thus, frequency and the voltage regulation of the different system buses can be accomplished. So, you do not have a problem on that. So, ultimately you supply to the main grid, since main grid is rigid. So, frequency is rigid. Accordingly, the similar to conventional distribution system, the microgrid units in the grid connected microgrid system can be controlled and modeled as PV and the PQ buses. That is a traditional state space analysis. The nominal operation of microgrid is connected to the medium voltage distributed grid being either partially supplied or injecting some amount of power to it. Depending on the demand request, the grid connected mode, the main grid and the local grid may send power to the loads. As this MV grid sets the root mean square RMS voltage, all DGs inside the microgrid can only generate current, but can be dispatched by the microgrid central control in order to provide the voltage references or the power references. So, it can be the both. The control system of the local control of the DGs is known as PQ inverter control and is said to be operating in the PQ mode. Today, a large centralized facility provides most of the electrical power around the world, which is fossil fuel, nuclear and the hydel power plant. These plants have good economic scale, but usually have to transmit electricity to the customer far away and hence affects the environment negatively, and also it increases the carbon footprint, etc., etc. You know very well. And using this renewable energy and DGs are installed near to the customer and reduces the relatively electric power losses on the transmission line. So, there is no hooking theft, something like that. Transmission line, because electricity is generated every close to the point of the end use. This also decreases the size and number of the power lines that must be constructed. So, if you want to dispatch power, you would want to have a standby line and all those things, that will have a extra cost. The renewable energy sources or distributed generations appear as the fastest, installation is very fast and less expensive option to the construction of the large or the central power plant with high voltage transmission line. This is the advantage of the microgrid. They offer consumer the potential for lower costs, higher service reliability, high power quality, increased efficiency and energy dependency. Use of RES technologies and green power can also provide a significant environmental benefit due to less emission. So, that is actually help us to reduce our carbon footprint, and the distributed generations are structurally divided into two types, conventional DGs and the inverter based DGs. This general control mechanism for controlling these DGs when they are used in a microgrids are explained in the next section that we are going to discuss now. So, industrial microgrids are relatively small power system that can be powered by only the single AC generators, and which is driven by the gas turbine or the diesel generator that we have seen in our household applications. The frequency of the AC generator is directly proportional to the speed of the rotating electric field. Hence, the power management lies on the isochronism speed, that means they have to rotate at a constant speed control, which keeps the turbine speed and a constant operation. The energy being admitted to the prime mover is regulated in response to the load change, which being tend to cause a change in speed. The control mechanism for the gas turbine, it is been shown in the next figure. So, this is the natural gas which you are burning. You have a speed controller. So, you have a reference speed regulator and reference measure speed. You have a PI controller, ultimately you will change the input of the throttling valve. You have a turbine or the compressor, and that will be actually generating the generated torque, and that will rotate the crank, and you have a field winding, and you have a air flow that will actually control also the flow, control the fire into the turbine or the ignition of the turbine. So, VREF is basically you have a VREF, you have a V measure, then they are the PI controller, ultimately it is the Q reference, and then it is IF, and that will change this exciter of the, that is a supply to the field winding, that will be changing based on the voltage requirement, and that will be the output to the exciter. In case the load decreases, the speed increases. The kinetic energy in the large inertia contributes to compensate the speed within the few instants. Moreover, energy is quickly admitted to the prime mover to maintain the speed of the speed at the set point. The speed regulation is using a simple proportional controller, since it is a mechanical controller and it is quite slow in operation. Any decrease in the load increases the speed, but energy is quickly reduced to the prime mover to maintain the speed at a constant point. An automatic voltage regulator, that is called AVR, is used to control the output of the RMS of the machine by regulating the voltage across the field exciter VREF. In case of the load change in the network, the power system inertia can perform the energy balance with detection of the variation in the system frequency. That is the way it will operate. Now, fast dynamic storage unit may be provided, that can be battery or ultra capacitor. The amount of the power required to balance the system following disturbances are significant during the load change. So, it can be flywheel, it can be battery, and depending on the kind of energy it will fluctuate. The storage unit must act as a controller of the AC sources for the face the sudden system changes. Now, let us come to the inverter based distributed generator, and this system has got an inertia and takes a lot of time to have a control, but this system is a low inertia system. You can act very fast, but there is a problem in it. Most DGs are not suitable for direct connection of the electrical network, and since it is a, for example, if it is a solar, it is generating DC, and if your gate may be AC. Therefore, power electronics interfaces are required. Most of the conventional most conventional power electronics topology is the back to back structures of these two current source converters for generator side converter and for the grid side converter. This is a two converter. The PV generator and the wind applications, for example, the generator side converters are usually controlled to implement the maximum power point tracking of the MPPT. So, you have seen the MPPT tracking for the wind as well as solar. So, and the grid side converter is usually the 3-phase inverter, and that will be connected to the grid. The power electronics converters can provide more flexible operation with high dynamics compared to the direct action of the synchronous or the induction generator to the grid. For a grid connected mode, the AC voltage and the frequency are supplied by the grid. So, all dispatchable DGs or distributed generator inverters must be controlled in PQ mode to inject power into the system. We have discussed PQ mode in previous in few lectures few slides ago. So, please revisit that timing. In the islanding operation mode, the inverter must control the RMS value of the frequency of the AC voltage, and it is called VSI mode. Now, with the grid following strategy. So, this is kind of strategy, let us understand. The grid side converter can control the voltage across the DC link capacitor and control the exchange of the active power with the grid. So, this is with the grid following strategy. This is useful strategy for non-dispatchable DGs or the renewable energy sources such as wind and PV generator, which due to uncertainty of the primary energy source cannot be enabled to correct the DC bus voltage control. So, this is something sometime happens. So, you have a primary energy source has some problem. The mechanism of the grid following strategy for the PV for the solar with a variable DC bus voltage, it will be shown little later, and functions such, and this function can also be done by additional generator side converter as shown in the figure 3. So, see, this one is essentially a grid following strategy of the PV generator with variable DC bus voltage for the MPPT. So, you have a solar panel, they have a capacitor, thereafter you got a input to the DC bus, and you sense this is a MPPT unit and this is a DC bus control, and thereafter you will have a power control. From there you have a reference of ID and IQ, where you allow this DC bus to fluctuates and you track the MPPT. So, thereafter you got a VDQ reference, IQ reference, you take, you measure this currents ABC and VC you convert to the DQ measures and IQ measures, and VQ and DQ goes here, and this will be compared fed to the PI controller, and thus this becomes your reference for the D axis and the Q axis. The grid following strategy is that with the variable DC bus voltage, this voltage is connected to the grid, and ultimately, so power will come and maintain this voltage here. Ultimately, you try to inject the power from that point, that is called the grid connect strategy. Another is grid following strategy, where you require to maintain the constant DC bus voltage and also the MPPT voltage. Then in this case you have a MPPT voltage, you will have a power control, that is switching signal, and you have a extra DC to DC converter, and thus your voltage here is fixed. And since there you have a DC bus control, you have a power control Q reference, that is IT and IQ, and you have a PI controller. From there you got a control over current, and similar thing is fed here. One advantage is there, you are maintaining a constant DC bus voltage, thus modulation index is fixed. Most of the cases, if you assume that grid side has a constant voltage, but here your modulation index will vary to give injection of the power. With the grid following strategy, using a choke filter, the grid inverter is controlled as a current control source. So, that is the current control source it will acts. Direct and the quadrature component of the current are calculated by the Parkes transformation for the power calculations. Generated real power variations with the DGs causes the DC bus voltage error, which is corrected via the DC bus control by adjusting reference of the real power and injected to the grid. The reactive power output is also controlled using the PI regulator by adjusting the magnitude of the inverter reactive current output. So, this is something we will do. Then the inverter can operate with a unit power factor and can receive a set point of the micro GCC for the output reactive power. This is the mode of operation for the grid connected mode. And in a grid following mode, you see that this is a primary source and you have a PG reference and you have variable DC, and thus you have to maintain the MPPT control, and you will control also the DC bus voltage, and then you have a power reference, that is PREF and QREF. And now you take the inputs from your grid side currents and voltages, you feed this voltage element here. Please recall our previous lectures of modeling, and thereafter you have ID ref and the IQ ref, and you will feed to this and you generate VD ref and a VQ ref. Thereafter DQ and ABC to the converter control, and that will feed to the AC inverter. With the grid following strategy, the inverter operate by injecting the available power at the primary source to the grid, since this DC bus voltage is constant. The DGs, generally we operate in this mode, but we require extra DC to DC converter. And the distributed generators, with the possibility of the increasing and decreasing the amount of the primary power, an additional active power reference can be used by the local power controller, that is GREF. So, this one is GREF to make the generated active power variable. This kind of DGs are dispatchable and their control system known as the PQ control, and this has been illustrated here. Now, power flow strategy in a PQ mode. With the power dispatching strategy, the voltage of the receiving capacitor is maintained by controlling the generated power from the primary sources. So, this is the primary source. So, you got a DG system, you give a pulses, and this one we will try to maintain the constant DC bus voltage, and you sense, this is a line filters, you sense the currents, and thereafter this is a measured value of voltage and current, and thus you have a reference power, and you have a calculation of the voltage and current, and you got a reference power. Thereafter, you got a voltage reference in the grid side, and you will inject the, you will subtract that value, and thereafter you got a Q reference. Mind it, if sag does not occur, so this loop does not work. So, it will work, come into the picture if there is a voltage sag or swell or voltage disturbances sometime. So, then you integrate over it, and ultimately, and you got F and Q. So, you got a reference for 1 and 3 and 2 and 3, and then you feed it to the PI controller with this voltage reference U and voltage reference between the line 1 2 and line 2 3. Since it is a 3-phase 3-wire system, sensing to line voltage is sufficient. So, from there you feed it to the ABC to DQ frame, and ultimately it will feed to this in AC inverter. The primary source is responsible to this power demand in order to maintain the constant DC bus voltage. This is suitable for application with the controllable power generations such as hydro turbines, gas turbines, fuel cells, and cells as availability to the primary energy standard. So, this is the quite familiar, it has been practiced in many kind of operation, this PQ mode of operation. Now, the power dispatching strategy in the PQ mode. So, we require to dispatch power, that is the whole intention of this renewable energy sources. So, then the voltage across the DC bus can be considered as a constant, and we were maintaining constant by a DC to DC converter. The grid side converter can control the active and the reactive power output. This kind of DGs are dispatchable. The Q inverter control consists of an outer power control loop that calculates the current reference for the current controller inner loop. Just go back and you can check it. So, ultimately, here you have this controller, and so you are feeding it, and this is the PI controller. So, coil compounding, it is generating that. This control scheme is similar to the isochronous speed of control in case of the classical DG. So, it has a synonymous in that sense, but it has got no inertia. So, this is one of the challenge of this speed control for the classical DGs, and the role of the DC bus is equivalent to the inertia, and is providing by the DC voltage constant. So, DC voltage constant, it is something like it is the capacitors. Please recall, you have a force voltage analogy. So, in there you have a voltage equal to, you can write, or you can have a force current analogy. So, in this case you can see that since it is a voltage control voltage source, so force current analogy comes into the picture, and thus in this force current analogy, capacitor is considered as a electrical mass. So, in this case this DC bus voltage will provide the required inertia. So, ultimately due to the current analysis, if you write current, so you will find that current is, you can, for RLC circuit, what you can have a current and the force analysis you can do. Then you will find, if you have a same kind of parameters coefficient analysis, you will find that mass in force will have a same kind of aspect in current, because it is C dV dt plus you can write it these equations V by R plus this thing. So, ultimately you can differentiate it, you can write in terms of the integration of it. So, mass and the capacitor will be synonymous here in case of the force current analysis, and thus in this case DC bus voltage will provide the inertia which is provided by this inertia by the rotating mass system. Thank you for your attention. I continue to do this classes on the modeling of the microgrid in our next class. Thank you.